Excellent. Well, thank you, Chris. Thank you for having me and giving me the opportunity to give this talk. I've been going to a lot of the meetups, and I've talked to a lot of you, and I have been excited to share a little bit about what I do with everyone. So this is my first cut at it. So let me first introduce myself and give you a quick background on what I do. So my background is actually, I'm not a data scientist really. I'm a hardware engineer. I came through as a graduated with electrical engineering degree and actually started designing electronics for a long time. Started off doing stuff for a long career at Hughes, doing satellite communications, designing circuit boards and chips and systems. And it's only recently, as with a lot of you guys, that I got into data science. Not because I'm personally aspiring to be a brilliant data scientist, but because I see data science having a lot of great target applications for the kind of stuff I'm really passionate about, which is computer architecture and being able to use novel hardware to accelerate algorithms, which is what I'm going to talk about today. So currently I work for a small company called Black Lynx, which is kind of what we do. Actually, we specialize in what we call heterogeneous computing, where we take different kinds of devices, CPUs, GPUs, FPGAs, and combine them together in the right way to accelerate algorithms and solve problems for customers. So it's a great team of engineers here. I'm lucky to have the opportunity to work here. So let me get started then with, let's see. Slide is not advancing. Okay, this is just a little kind of high-level outline of what I'm going to be talking about. Basically, I first have to define what exactly do I mean by hardware accelerated, because we'll talk about algorithms, and well, algorithm is just a description of steps to follow. You actually have to run it on some kind of hardware. So, I mean, you're always running it on hardware. So, what does it mean, hardware accelerated at all? What I'm really talking about is how you map the algorithm to the actual particular hardware architecture. And I'm going to talk about the traditional CPU that we use everywhere. And I'm going to talk about some of the other types of hardware architectures that we can map algorithms to. And I'll talk about the pros and cons of the different ones. I'm going to cover, start off with the CPU, and then I'm going to talk a lot about FPGA, field programmable gate array, which is a type of programmable chip. And I'll talk a lot about that just because that's what I know the most and I spend a lot of time on. But I'll also talk about GPU, and I'll talk about ASICs, and the TPU from Google is one type of ASIC. I'll talk about how you can deploy these in a range of locations, from the cloud to all the way to the edge, and how you might choose which type of device you might actually use, and some examples, and also talk about some of the next generation kind of architectures and technology that I know about. So let me get started here. Let's start with algorithms, right? This is just kind of a high-level description of a lot of different kinds of algorithms that are used in different industries. And I won't go into all of them, but basically there's a wide variety of them. And every algorithm has its own set of challenges associated with them, right? Some algorithms are very high in compute. They require a lot of computation, multiplications, and linear algebra types of operations. Some algorithms are more, involving kind of customized data structures where you have to manipulate, shuffle bits around. For example, some of the encryption. Some algorithms are kind of graph-oriented, and you're dealing a lot with pointers and chasing pointers around and following those kinds of data structures. Some algorithms require large data structures, some don't. Some require a lot of data movement, some don't. So there's all across the board in terms of what kind of hardware do you need? Do you need a lot of memory? Do you not need a lot of arithmetic processing? Do you need a lot of networking? Do you need a lot of high-speed data links? So these are a lot of different algorithms that all have. Some of these have really been optimized on particular types of devices. For example, computer graphics, obviously the origins of the GPU are to accelerate computer graphics. Now it's being used for a lot of other things too. So I'm going to also mention that, I'm not going to go into the details of this slide because it's very busy, but a lot of the applications today involve machine learning, as you guys know. And machine learning is a whole nother class of algorithms that are often very compute intensive and require specialized hardware. So these are, you know, kind of a, I just pulled this off of the internet, but it's it's a whole bunch of different machine learning algorithms. And a lot of the focus today is on deep learning and neural networks because those have had a lot of the recent breakthroughs, and those happen to also be very compute intensive. Some of the other types of machine learning algorithms may not demand any type of specialized hardware, but some do. So I'll talk about that some more. So let's get right into the architecture then. So we have these algorithms and we need to run them on a computer, right? And the computer has some kind of hardware. So what does computer hardware look like? Well, most of us just use computers, regular traditional computers. They use what's called the von Neumann architecture, right? And this is a very, very basic diagram of what's called the von Neumann architecture, which is, you know, very old, and it describes how a computer executes instructions. So you have on the left is sort of the hardware structure. On the right, you see, you know, the program. The program is a list of instructions, and the list of instructions basically tell the computer what to do. And there's logic in the hardware. It's called the control unit that kind of reads in the program, you know, step by step, and that tells it what to do for each step. The step might involve reading data from the main memory. It might involve shuffling the data into what's called the ALU, which I'll talk about in a minute. That's the arithmetic logic unit that does computation. It might use these temporary storage registers here. It might move data in and out of devices, for example, like your keyboard or your mouse or your monitor. And the data itself is usually maintained in memory here as well. So the von Neumann architecture is just, you know, a very basic approach to doing computing, and, you know, it goes all the way back, you know, to, you know, a lot of the original computers. This has served us very well. There's all sorts of, you know, tools, you know, compilers and high-level tools built around the von Neumann architecture, which make it really easy to write programs in high-level languages. You don't really, you know, in the old days, you'd have to write stuff in assembly language, and that's very low level. That's what the CPU is actually reading from memory, but you don't usually do that today. Usually you write something in a higher level language, or even a high, you know, a library that's already got all the optimizations in place. So I mentioned the ALU. The ALU, I'll call it the muscle. The ALU is really what does most of the work in a CPU, right? It does all the computations, let's say, arithmetic, you know, addition, subtraction, multiplication, division, comparing, bitwise manipulations, indexing. And then a lot of, you know, processors will have a floating point unit, which will let you do arithmetic on not just fixed point data, but floating point. And for those of you that aren't familiar with the difference, a floating point number is sort of exponential notation, and fixed point is just, you know, a basic number of bits that represent a range of numbers, and they each have their pros and cons. A floating point is more complex, but enables a lot of applications. So and this is sort of like an evolution of the von Neumann kind of CPU microarchitecture evolution, just to kind of show you how far we've come. On the left here, we have, you know, a really old processor called the Intel 286, which some of you may remember. And you can see the kind of the general size of it. I won't go into the details of the block diagram, but you can see there's the ALU, and, you know, you can see the, let's see, whoops, didn't mean to do that. You can kind of see, you know, a lot of the same things that were in the diagram I showed before, but in a lot more, obviously more complexity. And we've taken this architecture, and every generation, you know, we try to get better. You know, 286, 386, Pentium, you know, Xeon, you know, where we are today. And how do you do that? Well, one original way of doing it was just make the clock go faster, right? I'll talk about Moore's law in a second, but Moore's law is, you know, the idea that you can double the number of transistors every 18 years on a chip. And really early on, you used to be able to crank the clock speed up every generation. And if you just make the clock go faster, instead of running at 100 megahertz, it runs at 150 to 200 to a gigahertz to 2 gigahertz. You make the thing go faster, but that eventually tops out. So there's all kinds of tricks that are done in CPUs. So this is a more recent one, the Intel Cascade Lake, which you can see how much more complicated it is. It uses all kinds of techniques which, you know, hyper-threading and pipelining and branch prediction, all these things that I won't go into, but if you know about computer architecture, you know that these are, you know, tricks that make the design more complicated, but they make it run faster. I'm also going to compare that to the one on the right, which is an ARM core, which is also a pretty modern one. This is called the A76, and I just want to contrast the ARM is what's called a RISC processor versus the older ones here, or sorry, the Intel ones, old and new, are both CISC. And without going into too much detail, CISC stands for complex instruction set computer, and RISC is a reduced instruction set. And basically, it's just a different philosophy. And RISCs have really taken off recently and become very popular because they're very efficient. In fact, the ARM is used almost everywhere. The ARM is like the biggest, you know, deployed chip there is. Your cell phones have it, you know, all your tablets have it. The Intel is more for your, you know, the Intel or AMD, or usually in your, of course, your laptop or your desktop or the data center. So, but the RISC tend to have simpler instructions and wider data words for whatever that means. I won't go in. We can, if people have questions about that, I can go into that, but I don't want to get hijacked on it. I just want to show you kind of where we're at today with CPUs. Let's see. So this is the Moore's law I was talking about before, and you can kind of see that, you know, the number of transistors on a chip has gone up exponentially. Everyone's saying it's topping out. It's kind of topping out. I mean, it's one thing that's certainly happening is the frequencies aren't going up anymore. You know, you can't really run the chips any faster because they're using so much power. You just can't dissipate that much heat. So what happens is they put more and more transistors on a chip, and then eventually you kind of have to deal with the thermal issues. And so the biggest trick recently has been using more cores. You know, instead of what I showed you here, these are just single cores. And what you do is you take this whole thing here and you put like a whole bunch of them in a chip, and that's a multi-core, and you run them in parallel, and that's how you get the thing to run faster. But then you have to have the software that handles the parallel execution, which is all kinds of stuff out there today to do that. So I mentioned the multi-core here on the left, and then there's also this cluster computing that's being done a lot today to say, okay, well, I want to not just distribute over multiple cores, I want to run over multiple computers or multiple racks of equipment, and there's these frameworks for doing cluster computing that allow you to do that. There's pros and cons to it. It's complicated, and but it's, you know, sometimes works really well depending on the application. So this is just you've seen this kind of slide before. This is like, why do we even want to accelerate algorithms? It's because, well, we have applications that are demanding it. You know, we have a lot of data that's being generated. We have a lot of those algorithms that I talked about before that we want to run, and more recently we have a lot of deep learning, and we need to accelerate deep learning to be able to do autonomous driving and to do all these other great things that we're doing today in artificial intelligence, machine learning, and data science. So now that I've talked about the CPU, I can talk about some of these alternative architectures that you may not be as familiar with. Well, most people here probably are familiar with the GPU because they're pretty widely used now for the deep learning. Before, you probably, and if you went back 10 years, you would just think of it as something you use to make your video games work on your computer. But now, you know, they're being used for a whole larger range of applications. But I'm going to talk about all three of these things. I'm going to talk about FPGAs a good amount, and there's two companies that make FPGAs, Xilinx and Intel. And Xilinx actually, there was just big news a couple of weeks ago that Xilinx is going to be acquired by AMD. So it's going to be AMD and Intel. The Intel FPGA used to be a company called Altera, and they were acquired a few years ago by Intel. So the industry is consolidating, no doubt. But what is a field programmable gate array? I'll tell you all about that in a minute. In the GPUs, which are, you know, dominated by NVIDIA, and also AMD makes them, and others. But we used to call them graphics processor units, but now we often call them GPU, which is general purpose on graphics processor unit, because we're using them not just for graphics, but we're using them for other types of things as well. And then ASIC, what is an ASIC? ASIC stands for Application Specific Integrated Circuit. And an ASIC is a specialized chip that's made for a specific purpose. Think about like the chip that's in your cell phone to talk over the 5G network. That's an ASIC. Or you know, maybe the video decoding chip that's in your set-top box. That's an ASIC. These are specialized chips that do specialized functions. And you can build an ASIC to do specific machine learning types of things. So like the big one here I'm going to talk about is the Google TPU, Tensor Processing Unit, which is an ASIC that was built by Google to specifically accelerate deep learning. And there's other companies, I'll mention some of them. All right, so I'm going to go right into the FPGA. For those of you who are not familiar, what is an FPGA? So an FPGA, they've been around for a long time, actually. They were invented like back in the 80s, and originally they were just used as kind of like programmable glue logic kind of chips. Like if you're building a circuit board and you need to connect some chips together and you don't have just the right function, you can buy an FPGA, can connect the chips together, and you can program it, and you program it with some logic to tell it what to do. And they were really small and they couldn't do very much, but you know, a long time, you know, a lot of evolution, many generations of FPGA, they've gotten bigger and bigger and bigger, and now they're like pretty much entire systems on a chip, and they're kind of, you can view them as, you know, sort of their own processors in their own right. So what is the fundamental building block of the FPGA is this kind of fabric on the left. We call it logic fabric and interconnect. So you can see there's three basic blocks in here. There's what's called a CLB, which stands for configurable logic block. There's some memory, which is like a little RAM, random access memory. And then there's something called DSP, which it's digital signal processing, but it's really just like a multiplier, dedicated multiplier. So the CLB, I have a little depiction on the right, a simplified version of it. All it is just like programmable logic. You know, you have 4 inputs, A, B, C, and D. You have a lookup table. You have a flip-flop, if you know what that is. That's a little storage element, and then you have an output. So the CLB, just, you can give it this is a 4-input lookup table. They have bigger ones. You can give it a logic function, and it implements that logic function. And it's completely programmable. You can program anything you want into this lookup table. And so the other key thing about the FPGA is this interconnect. The interconnect is also programmable. So basically the idea is you can build any circuit that you want out of this. You can build any logic. You just, you know, whatever it is, you design it, and then you create the program that goes into the FPGA to load the right values into the lookup table, connect them up appropriately, and you can implement a wide range of logic, and it's completely flexible. You can use the memories in any way that you want. You can configure them, you bank them up into small or larger RAMs. You can use these multiplies to accelerate any types of arithmetic that require a lot of multiplications because they're very optimized. So that's the kind of the key kind of value proposition of an FPGA, is that it's completely programmable, and you can build any sort of data or architecture that you want out of it. It's not rigid like the CPU here. This is completely rigid, right? This is hardened into a chip, and then the programming here comes in the form of the program that gets read in from memory, and it executes it. Here, the programming is in the form of the actual interconnects and logic functions themselves. It's like you're building your own chip. And in fact, FPGAs and ASICs are very similar in that the whole design process is very similar. You can design an FPGA, you can design an ASIC. The only difference is the ASIC, the interconnects are fixed, whereas in the FPGA, they're programmable. So there's pros and cons to that, which I'll talk about. And then the other thing to note is these FPGAs have gotten really big. So this is an example of a pretty up-to-date FPGA, the Xilinx UltraScale Plus VU9P. You can see it's got over 2.5 million logic cells in it. It's got 6,000 multiplier, DSP slices. It's got 47 megabytes of RAM. This is just static RAM inside the chip. This is not the DDR RAM, which is off chip, that you'd have, however many 64 gigabytes of external RAM. This is on the chip itself. And it's got really fast links to talk to the outside world. So it just gives you an idea of the scale of it. And here's a couple of examples of FPGAs that I've built. What you're seeing here is what's called a device view. So it kind of shows you sort of pictorially the the routes and the logic that have actually been implemented on a chip. So the big rectangle here represents the FPGA, and I've color coded it. So each of these different colors here, the red, the green, the yellow, and the pink, these represent processing cores that that I implemented. This is a pattern matching primitive. It does high-speed search through text. The one on the right is an object detection primitive. This is actually a convolutional neural network that's implementing the YOLO V2 object detection DNN model. So you can see the very regular structure on one on the right. This is actually building a systolic array, which I'll talk about in a little bit, to do the computation for the neural network. But this gives you a view of kind of, this is hopefully makes it clear that this is a real programmable fabric. You can put anything you want in here, and the tools route the design to use the resources that are available on the chip. Now, this is a slide that I got from Xilinx, so it's a little biased. They call the FPGA the ultimate parallel processing device. Now, let's talk about parallel processing for a second. So why do we care about parallel processing? Well, the key is, how do you make algorithms run faster, right? One way to make it run faster is to run the clock faster, like I talked about before, but another way to make an algorithm run faster is to make things run in parallel, which is kind of more and more what we have to do. And I talked about how the CPU exploits parallelism by having multiple cores, and there's some other things that the CPUs do to exploit parallelism, but it's kind of a rigid architecture, but you can do it. Here in the FPGA, it's completely flexible in terms of parallelization, because there's no predefined instruction set or underlying architecture. So when you build logic, you can make the data structures as big as you want. You can have customized bit widths, customized memory hierarchies, customized data paths. Basically, you can build it to whatever you want. So if your arithmetic doesn't require 16 bits and you only need 7 bits, you can build it with 7 bits. If you can pipeline different stages, you can take advantage of that. If you want to store things temporarily in memory, you don't have to go all the way out to a DDR chip. You can build a little RAM structure inside the FPGA, a dual port RAM, and you can have data flow through the RAM, and you can build as many of them as you want. So that's the key advantage. Oh, I didn't realize this was a...
Neil, can you hear me all right?
What's that?
Can you hear me all right?
Yes, I can.
So some of the questions coming into the chat, which I think you might touch on in the end of the presentation, are I think a lot of us don't do, we don't do low-level architecture optimization. Like we don't use Verilog and program FPGAs, and most of us never have. What's the cost and what's the potential speed up?
Sure. Well, I mean, FPGAs themselves are, they make a wide range of them, so the cost is quite variable. Like for example, Xilinx makes, they're going after a wide range of applications. So their most expensive chips are the ones that go into like the data center. And you actually can run an FPGA instance now in Amazon Web Services, and you can run one. Soon you're going to be able to run one in Azure. And so those FPGAs are on the order of thousands of dollars. Maybe the most expensive one, maybe $10,000 or something. So they're up there. They also make smaller, lower cost devices that are meant for like embedded devices. Maybe to go in an automobile, maybe to go in a camera, maybe to go in, one place they're used a lot is in like cellular base stations, because they do a lot of the signal processing. So, anywhere, I think probably the cheapest FPGA is maybe going to be, tens of dollars, and the most expensive one is going to be thousands of dollars. You can actually get eval kits if you are. I don't have a lot on this, but if some of you may actually be interested in tinkering with FPGAs, and if you are, get with me offline, and I can point you to some good resources on how to do that. You don't have to break the bank. You can actually buy, some eval boards for, similar to like the Raspberry Pi type, kits to start playing around. Does that answer the question?
Yeah, it definitely answers the question about cost. And I'm sure you're going to get to this at some point in your presentation, but I think everyone's curious about the speed up.
Yeah, I mean, I can't, it's hard to give exact hard numbers. I could show some comparisons, but basically, what I'm going to show later in my presentations, I'm going to show the benefits and sort of pros and cons comparing FPGAs to CPUs to GPUs, and you'll be able to see kind of what it really depends on the algorithm is the bottom line. Some algorithms are going to be way better in a CPU, some are going to be way better in a GPU, and some are going to be way better in an FPGA. It's really what it comes down to. There's no, you can't, it's a mistake to think that you can take any algorithm and accelerate it in an FPGA. That's not true. So.
Okay, and I'll be interested to hear from Janice, who I see we have in the chat. She does I know that she's probably the only one that does a lot of work with FPGAs and
absolutely, I'd love to hear
compute architecture optimization.
Talked to her a long time ago about what she was doing. It was pretty fascinating to me too. So I'm sure this is child's play to her, but I'd love to hear what she has to say too. So yeah, so this is just another diagram sort of illustrating the customizations you can do in an FPGA. You can make the data paths, you can parallelize things, you can make the bit widths whatever you want. You can you know, basically depending upon what algorithm you're running, you can make things optimized for that algorithm. Here's another example. This is a channelizer. So this is used in signal processing. So this is something you'd use for a radio frequency kind of you you might use it for cellular or for satellite or for any kind of radio. And you know, you basically, here you show an A to D converter is receiving signals, and you need to perform all these computations. These are signal processing. You mix it down to a lower frequency. You do some decimation, downsampling, and then you put it through an FIR filter, which is a finite impulse response. That's a signal processing block. And what comes out is in-band and quadrature. And these, so, you know, without knowing much about radios, this probably doesn't mean anything to you, but what I'm trying to show here is how you can do this in an FPGA as a data flow. The data can flow in here, go through the mixer, go through the integrator, go through the down converter, there's a decimation, go through the filters, and it can be pipeline, meaning that you know, you don't have to wait for the whole path to finish before you know you bring in the next data. Like you know, basically the notion of pipelining is that data kind of flows through here and is stored in intermediate places along the way. So all these blocks are busy all the time, and this is the sort of thing that's super well suited for an FPGA. Or an ASIC, because it's customized architecture, it's a customized data flow. These almost are exclusively in the domain of FPGAs and ASICs today. You would not even be able to do this on a CPU. It would not be able to keep up. So, although more and more, some of the modern CPUs are able to do a lot of radio processing. You may have heard something called GNU Radio, which is an open source, but still FPGAs are far better for it. In fact, at my company, we're working on with some customers on trying to accelerate GNU Radio using FPGAs.
What type of signal processing algorithms are involved in processing radio signals?
Yeah, it's pretty basic stuff. This isn't, it's a lot of filters. This is an FIR filter. A lot of filters. There's decimation, which is basically dropping every n samples. Or interpolation is the opposite of decimation. It's adding samples when you're transmitting. There's a mixer is translating the frequency from one frequency to another. So it's basically like a complex multiplier and then what's called an NCO, numerically controlled oscillator. You probably can tell I know a lot about this because I used to work in satellite communications. So sorry if I'm going too deep into it. I wasn't really intending to talk a lot about the nitty-gritty of radios here. I just wanted to show how that it's a good application for FPGAs.
Certainly, and I asked the question because I think a lot of people here aren't familiar with the FPGA aspect, but as data scientists, we are really familiar with the signal processing side of things.
Absolutely, yeah. So I mean, this is how I got into it, actually, Chris. You know, when the reason I used to work at Hughes doing satellite communication stuff, and we used a lot of FPGAs for this very purpose. And I started to see, hey, this thing is not just good for signal processing. You can use it for general purpose computing. And I started to get really inspired about all the different things you can do with it. So it's not, now I see, you know, machine learning stuff is also very well suited for FPGAs as well as a range of other applications. A lot of those algorithms I talked about earlier. Chris, you and I talked about the what some companies are doing with high frequency trading and the exchanges, and they're using FPGAs to get really low latency responses to place orders on the markets. So that's another application. They're used in the oil and gas industry for exploring. They're used in I mentioned the cellular, the data centers. I'm sorry, the base stations for cellular. So yeah, a lot of applications where it makes sense. So here's another way you can do parallelism, is that typically what you have an FPGA, not by itself, but you have what's called heterogeneous computing, where you have the FPGA and the CPU together. And so if you just ran on the CPU, it would look like what's on top. You'd have function 1, function 2, function 3, function 4. Sorry, that function 3 got messed up in the picture here. On the bottom, you can see what we've done is we've accelerated function 2 in the FPGA. So the CPU runs, it computes function 1, it hands off control to the FPGA, which processes the data faster because it's accelerated, and then it comes back to the CPU. And you can go even further with this. I don't have a diagram showing it, but you can also have the CPU and the FPGA working together at the same time. So whereas some of the functions are done in the CPU and some of the functions are done in the FPGA, that's true heterogeneous computing. And that's a common thing you'll do is find an algorithm, figure out which pieces of the algorithm were best implemented in the FPGA, and do those in the FPGA, and do all the rest in the CPU, and then build a system that exploits that. And we're doing a lot of that here. I think that's the same slide. I also want to talk about systolic arrays, which are very interesting and a very great way of getting a benefit from parallelization in an ASIC or an FPGA. So what is a systolic array? So maybe best illustrated through an example here. So this is a code for a matrix multiplication, and you can see it's a pretty compute intensive operation. It's order of n cubed, and the question is, how would you accelerate something like this in an FPGA? This is a very serial operation in a CPU. Now it can be parallelized. There's modern CPUs have vector processing, and so you can actually do pretty well in a CPU these days. But fundamentally, it's a serial operation. So I found this really cool animation. I'm stealing it from Google because it's from their. So if it says TPU, ignore that for a moment because it is a TPU. It's a systolic array in a TPU. So this is actually the Google Edge TPU, and they use a systolic array. And
so if you're looking at a different screen, you might need to switch the Zoom share to that screen.
Yeah, I think I got to switch. Give me a second here. All right, can you guys see this animation?
Yes.
All right, so this is just an example of how the TPU is processing data in a deep neural network, and you can see each of these, each of these squares is a kind of a processing node. We call it a processing element, actually. And so the data is getting fed in through the columns into the kind of upwards into the processing elements, and then the processing elements are doing kind of multiplications and partial sums, and then the data is flowing to the right, and you can see the results pop out on the right. So why is this so great? The reason this works so well is because if you can do this right, all of these processing elements are doing computation in parallel, so you can really get a lot of compute happening very, very quickly, very high throughput. And it's very efficient because the data doesn't have to come in and out of memory. It just flows across these processing elements. And so this is extremely well suited for an ASIC or for an FPGA because of that customized routing capability. Interestingly, you can't do this in a CPU, and even the GPUs, which we'll talk about, have tensor cores in them. They don't quite work like this. So let me share my screen back to the slides. Okay. How are things looking, Chris? Do we have any
All
questions?
good. I can see the PowerPoint.
Okay, great. So a systolic array is very useful. And here's another example of a systolic array. This is a real world example. It's called the Smith-Waterman algorithm. It's used for genome sequencing. I don't know a whole lot about it. We looked at this at one point, but you can see this is just another example. You can see on the left the systolic array and how the data is flowing through it. And it's really good for this type of algorithm. And then here is, let's get into neural networks then, because obviously we need to talk about that. So how would we do a neural network in an FPGA? Well, this is actually from Xilinx. This is their implementation of what they call a DPU, which is a DNN processing unit. And you can see at the heart of it is, look, voila, a systolic array. And the systolic array does most of the compute. This is a convolutional neural network. And then you can see that, basically data is fed into the array, the weights, which are, the coefficients. And then you have the actual input activations for a layer get fed into the systolic array. It does all the multiply and accumulation to implement the, one of the nodes in the neural network. And then the post-processing here, this is the adding the bias and performing the activation function, which in this case is a ReLU, rectified linear unit, and then the pooling. And then the results get stored back into memory. There's a crossbar switch here that controls the memory. So this is something that Xilinx built. We played with it. We have our own that we built here at my company. And this is a very efficient implementation. And what's nice about this compared to like a GPU is that it's completely customizable. Like if I have a neural network that requires a certain size, a systolic array, I can make it smaller, I can make it bigger, I can change the representation of the data, I can make it 8 bits, 4 bits, 7 bits. I can use floating point, I can use fixed point, I can put multiple instances of this accelerator in one chip at different sizes. For example, what if I have a data flow pipeline where I want to do object detection followed by object classification? Well, I might have a different neural network for the different model for the detection as I do for the classification. So I could, for example, build one of these that has just sort of the right dimensions and sizings for the object detection. I could build another one that's sized pretty well for the classification, and then I could kind of have them running both in the same chip and then a sort of a data flow pipeline fashion. So that's one of the benefits. And I talk about some of the optimizations that we can do in a neural network here. I won't go into all of them, but you've probably seen some of these. You can do quantization. Not mentioned here, but quantization is when you go from floating point to fixed point, and you use fewer bits to represent the data, and that requires a lot less computation and a lot less power. You can prune the network, so if you have a neural network and some of the weights are very close to 0, you can say, well, it's close enough, let's just make them 0, and you just pull the whole node out, and then after pruning, you've made the model a lot smaller. You can use techniques to compress the size of the model to make them smaller so they don't use as much memory to transfer in and out. These are algorithmic optimizations. Winograd is an FFT. You can use these depending upon the size of the convolution kernel. It might make sense. Like if it's I believe if it's a large convolution kernel, then the FFT makes more sense, and if it's a smaller one, the Winograd makes more sense. So you can optimize. So in terms of precision, this is a good chart that shows the different precisions. So you can see it's pretty wide range what happens when you have like an 8-bit, 16-bit, 32-bit. The top 3 are fixed point, and then you get into floating point. These are additions and multiplications, and you can see that the floating point operations use a lot more power than the fixed point operations. And you can see that a 32-bit operation uses a lot more power than an 8-bit operation. There's also a couple things on the bottom that talk about the memory accesses, right? So we have different types of ways to store things in an FPGA or in a CPU for that matter, right? We can store things internally in like registers. We can store things in embedded SRAM, which I talked about before, or you can go all the way out to the DRAM, DDR, You can see going out to the DDR uses way more power and is way slower than staying on chip. So, you know, you can try to trade those things off in your design. You can also see that there's cost to that. If you the fewer bits you use, the lower accuracy you have in your model. So this is a chart showing some examples of that. That, you know, if 8 bits is pretty good, then you get down 7 bits is not that much worse. You can kind of go all the way down to like 5, 6 bits, and it's not so bad. But if you start to drop down to 4 bits or 3 bits, performance really drops off noticeably. So, and by the way, some of the kind of embedded devices like the Google Edge TPU that I'll talk about in a minute, they use fixed point as well. So it's not just exclusive to FPGA, but the FPGA does let you really customize the degree of precision that you want to use. Okay, how do you program an FPGA? You're probably all dying to get started and you want to know how you do that. And I'll try to address that. It used to be really hard to program FPGAs. It's gotten easier. The real pros and the long timers use a special language. There's 2 of them actually. One's called Verilog and one of them is called VHDL, and it stands for these are types of what's called register transfer level. So it is a programming language, and it's very low level. It's even lower level than, like, say, C or C++. And you're really describing in this code the logic that's going to get implemented in the FPGA. So, you know, it's also a parallel language because the FPGA is parallel. So you have these, you know, like this always block here. You can have a bunch of always blocks and they all operate in parallel with one another. But a lot of the constructs are very similar to C. You'll see there's like a for loop, there's a case statement. So it's actually modeled after C, at least Verilog is. And you know, it has the concept of data structures, but it also has, because it's a hardware descriptive language, it has the concepts of inputs and outputs. So everything is organized around blocks and inputs and outputs. So that's, if you want to get the best performance and tweak the heck out of your design, you use RTL. But if you want to make life a little easier, you can actually program your FPGA with C and C++ now. There's tools for doing high-level synthesis where you take your C code and you can actually compile it down to RTL, and then the tools take it from there. So when you do it that way, it's not just, you don't just take your C code that you wrote for your CPU and put it on the FPGA. You can, but you probably want to tweak it a little bit. There's techniques where you put what's called pragmas in your code to kind of hint the compiler to tell it how to make the most use of the parallelism in the FPGA. The other thing I'll mention is this framework called OpenCL. OpenCL is a whole programming model for doing heterogeneous computing. It works not just with FPGAs, it also works with GPUs and other devices. And OpenCL is also its own programming language. And so the idea behind OpenCL is that you can create designs that are written in a high-level language where some of the code runs on the host CPU, some of it runs on the FPGA, and it has a whole dedicated API that lets you transfer data back and forth between the two and run your program. So it's a very, very flexible framework, and it's also nice because it makes your design really portable. Like you can write code for OpenCL, you can run it on one board, you can recompile it and run it on another board that may have a different FPGA or may have a GPU. So we've done a lot with OpenCL to allow our stuff to run on different hardware platforms. The last way to program an FPGA, and I'm almost done with FPGAs, thanks for bearing with me here. There is libraries, right? So Xilinx has been trying to make life easier for developers because they want people to buy their FPGAs. So instead of saying you got to write your code in Verilog or even in C, they built a whole range of libraries across different domain-specific domains. So there's stuff for of course there's stuff for doing deep learning. They have a whole framework where you can run TensorFlow or Caffe, and you can run those on the FPGA. They have stuff for finance. They have libraries for finance. They have libraries for video compression. They have libraries for signal processing. They have libraries for databases. So data security, like cybersecurity. So there's quite a big range of and they keep building on their libraries. So the idea here is that you can actually just, run one of these libraries, and then your code just runs in a higher level language. It could run in Python, and it directly calls the FPGA, and you don't have to understand what's under the hood. They take care of it for you. So that's going to be, I think, a more popular way going forward. And also, you can do it, across the domain. You can run your designs in the cloud, as I mentioned before. They do have instances in the cloud. You can run it on your own on-premise environment. They have edge devices that are a lot cheaper, as I mentioned before. So I think I'm wrapping up. Oh, last slide on FPGA. This is sort of a glimpse into the future. It's the present/future. I just want to kind of talk about where FPGAs are going. This is the latest architecture of Xilinx. It's called Versal, and they've really taken it a big step forward here, because they're recognizing that we need to do heterogeneous computing, that just having an FPGA fabric is not enough. Some things really do make sense to put in a CPU, and some things really do make sense to put in like a GPU type of architecture. So the latest generation, they divide the chip into 3 parts, right? There's, on the left, they call it the scaler. They actually have ARM processors in the chip. And then in the middle, they have what's called adaptable. This is the traditional FPGA fabric that I've been talking about, where you can program, the logic and the routes, and reprogram it as desired. And then this is a new thing on the right they created. They call it AI engines, but it's not exactly like a GPU, but it's a kind of a vectorized processor, a big array of them that are organized in such a way to accelerate things like neural network inference and also signal processing. And then there's all these links between them, and there's this big network on the chip that connects everything together. So I think Xilinx's idea of the future is that you can take your application and you can take your algorithms and you can split them up appropriately between these, scalar, adaptable, and intelligent. All right, finally, done with FPGA. Does anybody have any questions at this point?
Yeah, about the neural networks. You
Okay.
talked about FPGAs and neural network pruning, and you talked about how, a traditional neural network has a ton of interconnected nodes, but then when you prune it down, there's a certain number of significant nodes that actually contribute to the output of the model. What do you use to actually write the structure of a neural network to the FPGA? And when you do that, you must have an existing already trained neural network ready and in hand in order to do that, right? There's no concept of like a dynamic or retrainable neural network on an FPGA, or is there?
I mean, there's lots of different ways to do it. The examples that I showed were convolutional neural networks. There's also, other types of neural networks like Xilinx has an LSTM, for example, which is a different. It's really different. I mean, it's a different architecture in the FPGA because it can be. So it doesn't need to follow the same compute model. But one of the key things about the FPGA, as I mentioned before, is it's programmable, right? And it not only is it programmable, it's also reprogrammable. So, this logic here that goes in this adaptable region, you program it with your design, and then you can actually do some compute on it. And then if you decide, you want to do something else, you can actually load a new image into it. They call it an image, and it turns into another thing. Like you could have one neural network running, and then you could say, okay, I want to do a different network in my pipeline. So you can just load a new image into it, and the architecture, voila, turns into the new architecture and runs that. So it's basically the ones that we're looking at, that we don't hard code the weights into the FPGA. The weights are loaded into the FPGA dynamically. So you can have an architecture that you can run at one time with one set of weights, and then you can load another set of weights into it. Or you can load a whole new architecture into it. So it's very flexible in that.
That's what I was asking about. So there is some concept of adjustable weights or adjusting the parameters of the network after it's cast onto the FPGA.
Yeah, that's what we've mostly done, and that's what Xilinx has mostly done. I know there's research and there's experimentation with hard code. Like what if you could hard code the weights into the FPGA? say, okay, I know what the weights are. I'm going to make them, since the FPGA is programmable, I'm just going to make the weights part of the program. And then you can't change them without reloading the whole, FPGA image, but maybe it uses a lot less resources in the FPGA. Maybe you don't need all the RAM to store the weights because the weights are actually hard-coded now. You don't have to have a mechanism for loading them. So yeah, you see a lot of options are available, but the ones that I've seen are traditional in that you do load the weights into the design. I'll also mention that these things are really well suited for inference, but we don't really use them for training a neural network. Those are typically done on a GPU. And also, I talked about some of the optimization techniques like pruning and quantization. Those usually what you do is you would train your network, your full network with floating point, and then when you're ready to deploy on the FPGA, you go through this quantization process where you take a bunch of input samples and you run it through a calibration process where you try to optimize, because you have to scale things appropriately. Like if you only have 8-bit weights and 8-bit activations, you want to make sure that you don't go over the limit. You want to make sure you use that dynamic range really well. So, but you have the same thing, by the way, for GPUs and for TPUs that use fixed point. So it's nothing exclusive to FPGAs there.
Okay, that's very interesting.
So let's talk about GPUs. GPU is a different architecture, obviously, but it's incredibly widely used today for deep learning. And this is an example of a pretty up-to-date GPU, the V100 from NVIDIA. And you can see it uses its own form of parallelism, right? The name of the game here is parallelism. And so I already talked about how FPGAs can parallelize. So let's talk about how GPUs can parallelize. Well, what they do is they have these CUDA cores, and a lot of them. And the CUDA cores are like little compute engines. They also, the newer ones have these things called tensor cores. And they're really moving more and more towards tensor cores. I'll talk about what that is in a minute. They can do a lot of computations, and they're really big beasts. The model is quite different, though, between how a GPU works compared to a CPU or an FPGA. But the key thing with GPUs, it's highly regular, highly parallelized. It is a fixed data structure, unlike the FPGA. You can't change this structure. And this is sort of their newest GPU. The A100 is like an incredible beast. It's got so many cores, and they really, in this device, they've really focused on the tensor core. So here's a diagram that shows what's called the streaming multiprocessor. So the streaming multiprocessor is sort of the basic unit of computation in a GPU. And the streaming multiprocessor itself consists of what they call these warps. And then each of these warps consists of these cores. So some of these are CUDA cores and some of these are tensor cores. And so what's a CUDA core and what's a tensor core? Well, a CUDA core is like a little mini processor that, and the CUDA cores all in a warp, they all run the same instructions in parallel with one another. So if you've heard the term SIMD, single instruction, multiple data, I think I have a slide on that here.
I think we talked about that recently in our Python optimization talk, because that's what drives vectorization in Pandas and NumPy, is the SIMD.
Absolutely, yeah. It's the same idea, right? So SIMD stands for single instruction, multiple data. So if you really want to just parallelize something and it's very regular, you can just have a set of instructions that you run on a lot of data in parallel. And in the CPU, the way that's done is there's these vector extensions in the microarchitecture that lets you do, it's not anywhere near the same degree as a GPU, but you may be able to do a bank of multiplications or a bank of additions on data. But in a GPU, they take it a lot further. They have, each one of these CUDA cores is running in a particular warp, is running the same instruction in parallel, and there's like thousands of them. So they call it, instead of single instruction, multiple data, they call it single instruction, multiple thread, because you have a bunch of threads running in parallel, and it's sort of an extension of SIMD, but spread across these different CUDA cores. So that's the CUDA core, and let me jump to this slide real quick. This is kind of a programming model, and I'm not a GPU programmer. I'm not an expert in it, but I understand the concepts because it's very similar to OpenCL. OpenCL is sort of based on CUDA. It's just more, the CUDA is NVIDIA's programming model, and OpenCL is an open standard. But you can actually write OpenCL code and run it on an NVIDIA GPU or on another GPU. The CUDA only runs on NVIDIA GPU. So I mentioned the threads. So you have a thread, which is the computation you want to perform on the core. And then the way you parallelize it is you do a whole bunch of them in parallel by creating a thread block. They call it a thread block. And you run all of those threads on what's the streaming multiprocessor, which is this thing right here, across all these CUDA cores in parallel. And then you can also do multiple functions in parallel. They call it a kernel grid. So each one of these thread blocks is running a kernel, and a kernel could be a different function. So GPUs are not only used for deep learning, they're used for lots of other things as well, obviously. But you could run different kernels at the same time on the same device, and that forms the whole GPU. And then I mentioned the Tensor core. The Tensor core is kind of a special processing block here, and they've really beefed it up in this chip. I think this is actually out of date. I think this is the V100, so pardon me for having it on the wrong slide. But basically what a CUDA core is it's hardware that's specifically designed to accelerate matrix multiplication. So you know, here it shows that you take a 4x4 floating point 16 matrix, multiply two of them together, add a third one, and then create a multiply and add, and you get a floating point 32 result, and you could demote it to a floating point 16. So anyway, why do we have this? This is dedicated hardware to really speed up the kinds of matrix multiplications that you use in machine learning, particularly in deep learning training. So obviously NVIDIA dominates in that, and these tensor cores are a key part of that. But it's very different from the systolic array that I talked about before. It's really a different approach, but it does have a lot of parallelism. All right, I'm gonna move on to the TPU. Are there any questions about the GPU? I guess not. Okay, so the TPU, there's less information out there about the TPU because TPU is Google's sort of proprietary chip that they, you can't really just go out and buy a TPU board right now, except with the exception of the Edge. But the TPU, the original TPU and the TPUs that are used in data centers, they were developed by Google initially for themselves, and now I know you can use them on the cloud. You know, I think like with for example, what is that called? Colab. I think you can get TPU access. But basically, it's a dedicated ASIC for doing neural networks. It's probably pretty similar to the FPGA architecture that I showed you before with the systolic array, but it's hard-coded. It's an ASIC, and because of that, it's really, really fast. I mean, it's completely dedicated, and I think the first version of the TPU was fixed point only. It was only 8-bit multiply and adds, and I think the second generation added the floating point to it, and I think now they're working on a third generation. But you kind of get the idea here that, you know, Google has built this huge infrastructure of TPUs. They use them in their data centers for everything. You know, probably all your, you know, a lot of the stuff you do. I've seen, like, for example, Street View on Google Maps goes and it mines all the street data, and it finds like house numbers and stuff in it, and it uses neural, you know, it's running those on TPUs. So they do, you know, a lot of their research, like this, what is it called, GPT, natural language processing. They run them on a giant machine, just banks and banks of these racks of TPUs. So you know, they get to benefit from that. This is an architecture diagram. I won't go into this too much because I don't really actually know that much about it, but you can see that the key here thing is there is a systolic array. They call it a matrix multiply unit. And the rest of it is pretty similar to what I showed you in the FPGA, right? We feed the weights into it, we feed the activations into it. There's accumulators, there's the activation function, there's the pooling function, and it goes back into memory. This diagram looks an awful lot like the FPGA one I showed you. So, except, like I said, it's hard-coded. That's kind of the only other thing I'll say about the TPU is that you can get access to a TPU, a small version of a TPU. I don't think I have a slide on this, but my friend Steve Mulligan talked a lot about this in his presentation recently about some of these edge devices, and there's a Google Coral device which has a very small version of the TPU that you can use. I think it's only 8-bit weights and 8-bit activations, but they're cheap and you can play with them. All right, so I only have a couple slides here just on sort of contrasting and comparing the different types of devices. Since now that I've talked about all three of them, FPGAs, GPUs, TPUs, I can sort of try to compare them here. So this is comparing GPUs and FPGAs. So, as I said before, the GPU operates kind of like a SIMD. It's kind of a well-defined instruction set, uses fixed word sizes. It just runs a whole bunch of computations in parallel, kind of brute force. A lot of processing power, but it's really good for things that fit into that model. And certainly, deep learning fits very well into that model, and a lot of linear algebra types of functions fit really well into GPUs. Let's see. Well, then there's the CPU, which I skipped over, but the CPU is kind of like the good general purpose processor. It's really good. It's kind of like if you were to compare devices to cars, you'd say like the CPU is kind of like the family car. It's very versatile. You can put a lot of stuff in the trunk, and it's got you can fit your whole family in it, and it gets good gas mileage, and it's it kind of has all the basic features, but it doesn't exceed in any one of those things. It's just, whereas the GPU is like the sports car with like the really fast engine, but it's really good at one thing, going really fast for certain kinds of things, and it's not good for some other things. In the FPGA, I don't know if I have a good car analogy for FPGA, but the FPGA is probably, in some ways, it's neither like the CPU or the GPU because its architecture is completely customizable. So I think it's kind of the extreme in customizability. So if you have anything that's sort of unique, any type of computation where like the types of things that you see in the ALU, it really comes down to the ALU, right? I talked about the CPU has an arithmetic logic unit, and so does the GPU. And if what you're doing fits nicely in that GPU and in that compute model, it's going to be well suited for those devices. But if you have anything kind of special, anything with like data flow or pipelining or customized data widths or signal processing, those things work better in an FPGA because they just don't map well to the hardware that's fixed in the GPU or the CPU. And here's another one. This is specifically looking at deep learning. It's kind of the same things. You have these are the types of deep learning architectures. They talk about the CPU is really bad for deep learning, like really bad, because it doesn't really have a lot of parallelization. So it's just really slow. There's no way you can train any decent sized network on a CPU. I know that there are companies finding ways to take neural networks and prune them down and trim them down to be really small so that you can run them on small CPUs like your mobile phone and edge devices. And that's all great. You can do that. But anything heavy duty, it's not gonna be able to keep up. So the GPU, really well suited for that. The FPGA, they call that like a soft DPU because it's a deep learning processor unit, but it's soft, meaning it can be reprogrammed into different configurations. These are some companies that were, this is slide's a little bit out of date. DeFi was actually acquired by Xilinx. TerraDeep is another company. XDNN is Xilinx's core. And then hard DPU. Hard DPU is like the soft DPU, except it's hardened, and that's your TPU. And then there's these other companies out there and research projects that are building their own customized deep learning accelerator chips in an ASIC. I won't go into them because I don't know a whole lot about. I don't know that there's a lot commercially available yet at this point. I know that some of these companies got a lot of money and investments, like I think Wave Computing and GraphCore and Grok. So they're building all sorts of different kinds of chips. Some of them are for training, some of them are for inference. let's see, I'm almost done here. This is FPGA oriented, but I just wanted to show the versatility of these kinds of devices. I think this probably applies all across the board for CPUs and GPUs and even TPUs, is that you can run these things, you know, all the way in you can have like a really large scale system where you run it in the cloud and you use the high end GPU like the A100 or the B100, and you use a high end FPGA like the Versal I talked about before, or high end CPUs, you know, or you can go all the way to the edge and run, you know, smaller devices. These are Alveo cards, which you can buy from Xilinx, that you can plug into a small server. They also have embedded cards that are smaller than this. There's the edge devices we talked about, like the NVIDIA has some things like the Jetson Nano. Google has the Coral. On-premise is sort of in between, where you say I want to host my own server and I want to put my own cards in. So I'm just kind of show that you know, part of when you're trying to implement your algorithm, it's not just about what kind of devices you want to choose, it's where you want to put it, how you want to distribute the compute. There's a whole edge computing kind of industry kind of consortium going on right now, where companies are trying to figure out how to create, you know, edge appliances and edge devices that will complement the cloud and on-premise to kind of spread compute all across as we move into the world of ubiquitous, you know, 5G and IoT. So it'll be interesting. This is just a list of companies again. I just kind of threw this together. I mentioned some of them before. Some of the big players are doing it too, you know, like Apple. They're putting some kind of bionic chips in their latest iPhones. I don't even know what it is, but it's some kind of deep learning acceleration. Qualcomm is doing some stuff. I don't have that here. Some of the high-end research projects like these neuromorphic chips are pretty interesting. So it's the point I'm trying to make is the world of ASICs is pretty large. They're not quite so accessible to you and me, but there's a lot of companies and research groups out there doing interesting stuff. So I'm sure we'll see more of that moving forward. And that's all I have for my presentation. So thank you for hearing me over talk FPGAs, but give you a little flavor of what kinds of things excite me. And for me, I'm really looking for, you know, I have the solution for the problem, maybe, you know, like I'd love, if any of you guys are doing any work where you're looking for help with how best to accelerate something that you're doing and using the, you know, unique hardware architectures, I'd love to talk to you about it. For me, it's sort of a bottoms up. I like to fascinated with this technology, and I like to see how it can be used to enable new things.
Thanks very much, Neil. And this is really interesting and really impressive. We got about 15 minutes still, so we'll open it up for questions and general discussion.
Hey, Neil. It's Steve.
Hi, Steve.
Can you hear me?
Yes, sir.
Quick question. Tell me if I've got this right. The only by using the FPGA are you going to create a device that you could run off a battery? Is that correct? I mean, don't the other ones have too high a power requirement?
Well, I mean, I think it depends. I think power requirements, it's the same thing, Steve. It's like there's a whole range of FPGAs, and there's a whole range of GPUs, and there's a whole range of ASICs. So and CPUs for that matter. So yeah, there are small FPGAs that you could run off of a battery. Those data center ones I was talking about, though, they use a lot of power, so they're not gonna. I will say that we've been pretty good here about one of the things that we're doing at my company is trying to look at some applications where we consider what's called the swap size, weight, and power. So, you know, we have some customers that are interested in putting things in space, like in a low Earth orbit satellite, or putting things in drones, and they want to be able to do. They want to be able to, like, you know, have cameras or radar and collect imagery and do, you know, processing on that. Not have to transmit all the data back down to a data center, but be able to process it right there at the edge. And to do that, we're accelerating using FPGA, and we need to get the power down, right? You can't put a big data center up in a satellite. So yeah, we definitely have we've compared our you know, for example, that YOLO V2 thing I was showing you before, we were able to get that down to like 30 frames a second at like, I think like 50 or 60 watts, compared to the GPU was like 100 watts in that case. So FPGAs can be lower power, but it just all depends on what, you know, the thing with any of these devices, the program that you run on it does definitely affects how much power it's using, especially with FPGAs. And so, but some of those edge devices that you were looking at, I mean, they're going to be the lowest power things available, Steve.
Yes, but all the NVIDIA ones, you have to plug in somewhere.
Yeah, I mean, they don't run off of like a, you know, they don't run off of a regular household battery, if that's what you mean. Yeah, I mean, I think like some of the compute sticks, like the Coral has a compute stick, you can plug that into a USB port. It gets its power off of the USB port, for example.
Yes, that's correct.
I was going to try to find an example of, well, keep talking. I'm going to find an example of a smaller FPGA board.
Well, Neil, I can ask you a specific question then, because I have, I don't know if you've heard of a Snickerdoodle. It's a Xilinx FPGA with 2 CPU cores on it. And I was going to ask you if you could repeat the name of that library of the components that you can sort of,
yes,
the pre-built components.
It's called Vitis. I'll put it in the chat. See if I can get. Yeah, Vitis is Xilinx's. That's their latest software, and they have a growing list of libraries for different functions. There it is. I don't know about this Snickerdoodle thing you're talking about, but yeah, Xilinx does make a chip called the Zynq, Z-Y-N-Q, and it has it's meant for embedded application. So it's lower power. It has an ARM core in it, and it's got some programmable fabric logic in it, traditional FPGA logic.
Can you give us a sense of the development time required to transport some or optimize some algorithm by putting it on FPGAs? Because it's something we talk about in data science a lot. And I talked about a lot in my my Python optimization lecture was, you know, when do you have time to actually make an algorithm multi-core, and when is it worth it? So the question of when do you have time or the skill to make something FPGA optimized, and is it worth it? How do you answer that question?
Yeah, that's a fundamental question. I mean, now let's get practical here. I went into a lot of nitty-gritty technical detail, but at the end of the day, you have an algorithm you need to implement, and you want to get it done. And you know, you want to get it done quickly and efficiently. And so what's the best way to do it? Well, the fastest way to go about doing something is going to be to try to run some existing library that you can find. You know, if you can run on a CPU using, like I know you use scikit-learn, for example, for what you do. So obviously that's all pre-built, ready to go, you know, easy to parallelize. So yeah, if you want to get something done quickly, if you can find a library, if it's fast enough to run on a CPU, then that's great. If you need to get some improvement from there, then the first step would be to try to make it run faster on the CPU, because that's relatively quick, I think. And so you would do that next, assuming you're not concerned about power consumption. But then if you're worried about power and size, then that's a whole nother set of trades. But let's just talk about getting the thing done. Then if you need to go beyond that, if the CPU is still not fast enough for you, then you need to start considering you know, other kinds of devices. You know, that's assuming you don't want to go like, you know, cluster computing or anything. You know, you could do cluster computing, Or you can say, okay, can I make this thing run faster in a GPU or in an FPGA? And then it depends on what it is. I mean, if it's deep learning, then it's pretty obvious that it's going to be pretty easy to run on a GPU because NVIDIA's got that whole, framework all ready and easy to run. You can move from a CPU to a GPU almost seamlessly there. If it's something else, then yeah, I would try to find libraries. See who has a library for something on a GPU or on an FPGA, and see if you can use that first before you go and start writing the low-level code for something, right? And then only then, if you still can't get what you need there, then you have to start thinking about writing your own code. And if it's a GPU, you're going to be writing a CUDA code, and if it's an FPGA, you're going to be using one of the ways I talked about, OpenCL or C. I would try to use C or C++ or OpenCL high-level synthesis first, because you don't want to have to go through the learning curve of learning how to write RTL low-level code. It's only when you really want to get the absolute best performance on something then you would do that. So I would say, you can always reach out to me. I'm generally curious guy. So if anyone has any, stuck at a fork in the road and is looking for advice, I'd love it if you want to bounce it off with me. I'd be happy to give you my insights. But I think generally, as I've been doing this for a long time, I've built and developed a lot of systems, and I know that definitely you don't want to. Sometimes the optimal way is not the best way. The best way is the way where you can get it done in a reasonable amount of time, where the code is manageable. If you write something in really low-level code and then later you decide you need it to be different, you have to go back and rework that low-level code. That's not very good, So, whereas if you write it in a higher-level language, it's much easier to change.
And that's interesting on that note that you pointed out. For deep learning, you're going to use FPGAs mostly for inference or the prediction step rather than the training step. And I would, as someone that's worked with deep learning a lot, I would say that makes sense based on my understanding of which matrix operations happen when in that process.
Yeah, I think so. I mean, don't get me wrong. There has been research in doing training on FPGAs as well, and maybe someday we'll be doing that. But I think the GPUs are just so well suited for that, and they're just big. Especially these newer ones are just big beasts, and they just can crank through so much data and do so much processing. And it's a pretty well-defined operation. So for now, I haven't heard of anyone doing any training on a neural network other than either a GPU or a TPU.
Interesting. Do we have any other questions before we wrap up? Okay, if we don't have any other questions, we'll wrap it up. Thank you very much, Neil, for coming on and sharing all this information with us. For anyone asking about slides and recordings, as usual, I'll get the recording up. If Neil sends me the slides, I will post them somewhere, but I think the recording's probably the best. And I'll share it on the Meetup page for y'all.
Thank you, Chris. Thank you, Neil.
Thanks, everyone. It's been a pleasure.
All right. Thanks, everyone, for coming. We'll see you next time. Thank you.